Freeze this thought. A city, shrunk to 20 kilometers. A teaspoon here weighs a mountain. Time slows. Light bends back on itself. Meet the strangest object we can touch only with math. A neutron star. What it does to matter, space, and time will break your intuition. It begins with the end of a massive star, one far larger than our sun. For millions of years, it burns, fusing lighter elements into heavier ones. But eventually, its fuel runs out. The outward push of fusion fails, and in the supernova's last violent beat, gravity wins an absolute victory. The star's core collapses in on itself in less than a second. Electrons and protons, the fundamental building blocks of atoms, are crushed together, forced to merge into a sea of neutrons. The core rebounds in a titanic shockwave, blasting the star's outer layers into space. What's left behind is an object heavier than our sun, yet compressed into a sphere only about 20 kilometers wide. The scale is almost impossible to comprehend. If you placed Earth beside this 20-kilometer sphere, our entire planet would look like a continent next to a city block. Yet that tiny, city-sized object contains more mass than our sun. It is a cosmic paradox. Immense, yet minuscule. This compression leads to a density that defies intuition. A single teaspoon of neutron star material, if brought to Earth, would weigh billions of tons, as much as a mountain. The surface gravity is equally fierce, 200 billion times stronger than Earth's. If you could stand on its surface, you would be flattened into a one-atom-thick layer. A 1-second fall from just a meter high would accelerate an object to a significant fraction of the speed of light. Light itself struggles to escape this gravitational prison. Near the surface, gravity bends the paths of photons so severely that you could see the back of the star from the front. Time itself slows down, a direct consequence of Einstein's general relativity. A clock on a neutron star would tick noticeably slower than one on Earth. Many neutron stars are born spinning rapidly, their magnetic fields amplified to incredible strengths. These fields channel particles into powerful beams of radiation that blast out from the magnetic poles. As the star rotates, these beams sweep through space like a cosmic lighthouse. If one of these beams happens to sweep across Earth, our radio telescopes detect a regular pulse. We call these objects pulsars. The fastest, known as millisecond pulsars, spin hundreds of times per second, faster than a kitchen blender. Their rotational stability is so precise, they rival our best atomic clocks, making them invaluable tools for testing physics and even for potential deep space navigation. Then there are the magnetars, the most powerful magnets in the known universe. Their magnetic fields are a quadrillion times stronger than Earth's, so intense they could wipe a credit card from halfway to the moon. The immense stress of this field can cause the star's crust to crack and shift. These are starquakes. When they happen, they unleash colossal flares of X-rays and gamma rays. One such event released more energy in a fraction of a second than our sun has in 250,000 years, a burst of power felt by satellites across our solar system, from a star halfway across the galaxy. What lies beneath the crust is even stranger. Inside, the immense pressure and temperature allow neutrons to behave in ways impossible anywhere else. They are thought to form a superfluid, a state of matter with zero viscosity, flowing without any friction. Protons, meanwhile, may form a superconductor, allowing electrical currents to flow forever without resistance. Sometimes, the star's rotation suddenly glitches, jumping to a slightly faster spin. This is believed to happen when vortices in the superfluid core, which have been pinned to the crust, abruptly snap free, transferring their angular momentum to the star as a whole. The crust itself is a realm of bizarre physics. Just below the surface, atomic nuclei are squeezed together so tightly they can no longer hold their spherical shape. They merge into strange, elongated structures that physicists whimsically call nuclear pasta. Depending on the depth and pressure, they form shapes resembling spaghetti, lasagna, or gnocchi. Calculations suggest this nuclear pasta is the strongest material in the entire universe, millions of times more resistant to breaking than steel. A neutron star doesn't always live in isolation. If it has a companion star, its immense gravity can siphon off gas. This stolen material doesn't fall straight down. Instead, the star's powerful magnetic fields funnel it into glowing hot columns that crash down onto the magnetic poles. These hotspots, heated to millions of degrees, become so incredibly dense that the material can ignite in a runaway thermonuclear explosion. It flashes in a brilliant burst of X-rays, releasing immense energy in seconds before the star cools and the process begins anew, like a cosmic forge at night. By watching these X-ray flashes and timing the pulses from pulsars with incredible precision, astronomers can begin to map these alien worlds. Tiny variations in the arrival time of the pulses can reveal the presence of mountains on the crust, perhaps only millimeters high, but dense enough to slightly warp the star's shape. We see patterns in the light that hint at currents deep below a surface no human hand will ever touch. Near these surfaces, space and time are not fixed concepts. They lean toward the star, distorted by its mass. Photons climbing out of this deep gravity well lose energy, their wavelengths stretched, making them appear redder, a phenomenon called gravitational redshift. Clocks tick slower. Gravity is no longer just a force. It is the landscape, written on the very nature of light and time. Then there are the most cataclysmic events of all, collisions. When two neutron stars in a binary system spiral toward each other, their dance sends ripples through the fabric of spacetime itself. These are gravitational waves, and as the stars get closer, the waves become a crescendo, a chirp heard by detectors on Earth. In the final moment, they meet, and their merger blooms into a kilonova, an explosion 1,000 times brighter than a standard nova. In that incandescent fireball, the universe's heaviest elements are forged. The extreme conditions of the merger, a maelstrom of crushing gravity and torn-apart neutrons, provide the perfect environment for the rapid neutron capture process, or R process. This is where much of the gold, platinum, and uranium in the cosmos are created. The rare elements we wear as jewelry and use in our electronics were minted in the heart of these seconds-long, galaxy-shaking collisions. But what lies at the very heart of a neutron star? This is one of the greatest unsolved mysteries in physics. Deep in the core, the pressure may become so overwhelming that even neutrons themselves break down, their constituent quarks and gluons dissolving into a new, exotic state of matter, quark matter. This is still a theoretical possibility, a tantalizing hint that we have not yet reached the final chapter in the story of what matter can become under the most extreme pressure imaginable. We can never visit these objects. Instead, we observe them from afar, using an array of incredible instruments. We measure their pulses with radio telescopes, acting as surveyors of spacetime, letting the precise timing of their signals reveal their mass and radius. Our observatories are tuned to their cosmic whispers. X-ray eyes watch for accretion hotspots and violent bursts. Radio ears listen for the clockwork rhythm of pulsars. And our newest sense, gravitational wave detectors, allows us to feel the vibrations of spacetime when these giants collide. Each instrument gives us a different piece of the puzzle, all listening for the secrets of a city-sized sun. The more precisely we look, the weirder, and yet, the clearer, the picture becomes. We see superfluids flowing without friction, starquakes that shake a galaxy, and lighthouse beams that keep perfect time across thousands of light years. Neutron stars are not just dead stars, they are cosmic laboratories, written in the language of gravity and light. They are natural experiments pushing matter and energy to extremes that test the very laws of physics we trust, forcing us to confront the limits of our understanding. In their violent birth and bizarre existence, they turn stellar death into clocks, forges, and beacons. They are constant, humbling reminders that the universe is far stranger, more violent, and more creative than our imagination. We live our lives in the gentle, steady glow of a warm, stable star. It's easy to forget the extremes that lie beyond our quiet corner of the cosmos. But out there, in the vast darkness between the stars, city-sized suns spin, flash, and collide. And still, we look outward, driven by an insatiable need to understand. A lone pulsar blinks, a steady, rhythmic heartbeat in the cosmic silence. Each pulse is a message from a place we can never go, a testament to the profound and beautiful weirdness of our universe. It is a call to both wonder and humility.